Okay, number one. This diagram is of a microwave traveling through a vacuum-free space from point A to point B. They've given you the distance between these 2 points, but they want you to calculate the wavelength of the microwave. Now, the first things we need to do is to look at the diagram and decide how many complete waves do we fit between A and B. Okay, so a complete wave is this. So that's one complete wave. So we've got 2 complete waves, we've got 3 complete waves, and then we've got an extra half as well. So we know then that the total distance is 0.6 meters. Okay, but that is for 3.5 waves. So if we want the distance of one wave, we divide that by 3.5, and we get 0.17 meters. Okay, so that's the wavelength of the microwaves. It then asks us to state an equation that links speed, frequency, and wavelength. Well, wave speed is equal to frequency times wavelength. An equation you need to know. And then you're going to use that equation to work out the frequency of the microwave. So we're going to rearrange this. For those of you who like your triangles, on the top of the triangle we're going to have wave speed, frequency, and wavelength. So frequency then is going to be speed divided by wavelength. Put our values in. Our speed is given in the question here. It's the speed of light because all electromagnetic waves go at that speed. 3 times 10 to the power of 8. And we're going to divide that then by the wavelength that we worked out in the previous part here, 0.17 meters. Now if I do that calculation, I get quite a large number. Now rather than writing it all out and putting all the digits the calculator gives me, we're going to round it to 2 significant figures is probably most appropriate here because the data they gave us was to 2 significant figures. So I'm going to say it's 1.7. I'm going to put it into standard form times 10 to the power of 9. And that's a frequency, so it should be measured in hertz. The next part of the question is looking at radio waves and microwaves as they move past a hill. Now the radio waves have got a large wavelength. We can see that here from the diagram that the wavelength is the distance between these wavefronts, while we've got a small wavelength here for the microwaves. The radio waves are much larger wavelengths. Now they said name the effect shown by the radio waves in the diagram. Well, the radio waves are bending around an obstacle, so hopefully you can see that this is an example of diffraction, where the wave direction has changed as waves pass through a gap or around an obstacle. Now, all waves diffract, right? But you can't really see much diffraction, or it doesn't appear to be happening, in the second diagram. So you've got to suggest why this effect is not shown by the microwaves in diagram 2. And the first key thing is that the microwaves have got a shorter wavelength than the radio waves. Okay, they're both electromagnetic waves, they're both very similar. The one key property that's different is going to be those wavelengths. And diffraction is only going to occur when the wavelength is comparable to the size of the barrier. Just like with the gaps, where you send waves through a small gap, it's only going to diffract noticeably if the wavelength is around the same size as the wavelength. Well, here, the gap, the wavelength is so small that as it travels around that gap, you're not going to see any noticeable diffraction.